Thank you. So good morning, everyone. I'm actually not Michal Beneš. I am Pavel Strachota. Michal Beneš sits over there in the audience. But I hope that won't be a problem for presenting our multiscale model based on first principles for simulations of lithium-ion batteries. This is a collaboration, or these results were created during a project with Honeywell Prague laboratory, which unfortunately doesn't exist anymore nowadays, but the head of the group at Honeywell was Professor Vladimír Havlena, who's still in the business. He's active at your faculty, at the Faculty of Electrical Engineering. And myself and Michal Beneš and some of our students come from the Faculty of Nuclear Sciences and Physical Engineering, from the Department of Mathematics, and more specifically from the Mathematical Modeling Group. Today this presentation is actually designed for a bit longer talk, so I'll have to be quick. I will present a mathematical model that tries to simulate the electrochemical processes that take place directly in the porous structure of the battery, in the electrodes, and in the system from the physical point of view. And also I will go through it quite quickly. And in the next part, I will present the scenarios that we use to validate the model and what kind of results we can have, either from like short-term behavior, which means like one charge and discharge cycle, and also long-term behavior where we try to model aging or degradation processes in the battery. As for the mathematical model and physical model, I know that most people are familiar maybe with this, but still maybe there are some visitors that are interested in the physics. So most cells, especially these kinds of like cylindrical cells, are composed of wound layers, where each of the layers, or actually the layer of consists of two electrodes separated by a thin layer, which is called a separator. At both parts of the electrodes, there are the current collectors, and the electrodes are composed of porous material, which is filled with electrolyte. And so for example, during discharge, the lithium ions, cations or ions, are released or de-intercalated at the anode. They move through the electrolyte, through the separator, into the porous material of the cathode, and then they are incorporated into the solid material of the cathode again. So from the microscopic point of view, both the anode and the cathode can be represented like kind of, this is of course a simplified model, but kind of spherical particles, where the lithium ions enter actually through the surface of the particles, and then they can move toward the center, or vice versa. So there is a concentration of lithium ions inside these particles, and of course the lithium ions can also freely move through the electrolyte. So our physical or first principles based model consists of the description of diffusion of lithium through the particles of the solid material in the electrodes, also the diffusion through the electrolyte, and also, of course, the electrical processes, which means the charge balance has to be satisfied in the solids, in the electrolyte, and the intercalation or de-intercalation, I don't like these terms, they are too long, but I mean the release and the incorporation of the lithium ions into the particles are governed by the Butler-Volmer kinetics. We also have some equations for the heat production and transfer, but because we only limit ourselves currently to the one layer of the battery, which is actually wound to form the cylinder, so the heat transfer actually is not accurate in this sense. And as for modeling the aging, we use equations that describe the formation of the solid electrolyte interface only at the anode and only during charging, which is caused by the parasitic reactions. So this is basically like the model is 1D, which means we are modeling the motion or the diffusion only across the layer, which means that we basically have a 1D interval, which is described by some part of the positive electrode, the separator, and the negative electrode. The second dimension actually is represented by the radial direction where the lithium ions enter and diffuse gradually into the center of the microscopic particles. Now there will be a list of quite a lot of equations which we won't probably have time to discuss in detail, but we have diffusion in the electrolyte, like simple diffusion equation, where the concentrations are the main quantities. Then we have, of course, because there are these three parts of the domain, so there are boundary conditions in between the positive electrode, the separator, and the negative electrode, and the fluxes of the material or of the lithium ions have to be consistent across these interfaces. So there are boundary conditions that describe that, this is a diffusion equation in radial coordinates that describes the diffusion of lithium into the center of the microscopic particles, or vice versa. So that's this one. There are also boundary conditions for the diffusion into the particles, which means, of course, for example, at the center you have no flux because there is no movement across the center. At the surface we have fluxes of lithium that are described by the Butler-Volmer kinetics. So this is just for the charge balance laws, which means basically Ohm's law, where phi's are the electric potentials. This is in the electrolyte. Sorry, it's been a couple of days since I last worked with this model, so we have it also in the electrolyte. And this is the Butler-Volmer equation that describes the fluxes at the interfaces of the solid and the electrolyte. So this is kind of an exponential formula, which in our model we have these anodic and cathodic transfer coefficients which are considered equal. So this expression is simplified a little bit, which is important in the numerics later on. And also, this is not actually important in our results, but we, as I mentioned, we also have heat transfer. So we have heat equation, and there are some source terms that describe the release of heat during charge and discharge. So I maybe skip this because it's not so important for us. What is important, however, is the description of battery aging, which is modeled by the parasitic intercalation overpotential, where we have parasitic fluxes that are actually, because of the parasitic reactions, there is a solid, there is an interface formed at the surface of the particles that hinders the transfer of the lithium ions into or out of the particles, which is caused by which actually has an effect of the increase of internal resistance of the battery, and of course also loss of active lithium ions, which results in the decrease of capacity. But for our applications, which are mostly the high-performance batteries found in electric or hybrid electric vehicles, actually the internal resistance is much more important, because even though you can maintain most of the capacity, once the internal resistance increases, then the batteries can no longer be used for electric vehicles. They of course, can be used somewhere else. For example, for households, we know that there are tendencies to use actually the depleted HEV batteries for electricity storage, for example, in households. This is the schematic of the reaction that takes place. This is the parasitic reaction, and this is the form of the expression that governs the parasitic current, which is only applied during charging. So during this charging, we have no parasitic reactions, although generally there are some, but they are much more important during the charging phase. Numerical simulation is also interesting because we have seen many papers on solving these kind of equations, but you can only see the results, but never any numerical method. The question or the interesting part is that actually if you consider all the equations and all the boundary conditions, it looks like the system is overdetermined. So it seems like it's not possible to solve it, but actually it is when you consider kind of integral formulation where you don't actually solve differential equations, but you solve an integral part of the equations by moving from the potentials that are actually finally they are actually excluded from the equations, and we solve the equations in terms of these integrals. And finally, we actually find this J by some kind of iterative procedure with the relaxation parameter omega, which was found to be very stable, even for very high currents, which are intrinsic for these HEV applications. We have basically a very simple finite difference method or finite difference grid, which is then used for integration as well. So this is just a 1D case, and it's for the spatial dimension. The same holds for the radial dimension that describes the diffusion in the microscopic particles. There are two time scales, one for the microscopic, one for the macroscopic processes, and the resulting algorithm, which uses implicit Euler integration in time, ends up to be 5 times or even 10 times faster than real time. So we are able to simulate the processes in real time. It's also convenient if you have battery aging experiments that take, for example, months, because you have to take hundreds or thousands of cycles with our algorithm. Of course, it's not immediate, but it takes considerably less time. Now I have probably have to speed up a little bit. So there are a lot of parameters. Some of them are found from literature. Some of them were determined for the specific cell that we had at Honeywell where experiments were performed. So I will just skip all these details. These formulas then actually determine the open circuit voltage, which is important in the model. And these are comparisons with literature, classical works by Dow and Subramanian. They for like a normal battery and very low discharge currents, we are getting a nice agreement. But for higher discharge currents, the results from by Dow, for example, are meaningless, obviously, because there is no internal resistance considered in the cell. Of course, there is always an internal resistance. So it is the dependence of voltage on time during discharge. So even at the beginning, the voltage, of course, if you are under high load, then of course the voltage has to decrease. But this is not reflected in the results by Dow. So our model seems to be better. And now we just did without the aging, without the parasitic currents, we did like thousands of cycles, or not thousands, maybe 1,000. And we see that the model is extraordinarily stable that the voltage curve is actually in the first cycle and in the 1000th cycle is exactly the same. Now we will see how it looks when we incorporate also aging. The validation was made by using the cells that actually appear really in the electric vehicles. The large batteries are really consisted from these small cylindrical kind of cells. This is, for example, Tesla, how it looks like in Tesla. And this is how it looks in reality. This is a Panasonic cell. This is not the one used in Tesla. And we used, for the experiments and for the evaluation, this is the battery that we used. This is the description of the open circuit potential for this specific battery, which was fitted from experiment, and then we could use discharge. Then we could employ our model to describe discharge experiments, just one cycle here. So at the very end of the discharge cycle, we have some disagreement, but for the most part, we are getting quite good results. And now for the aging, we had some quite a complex procedure for the experimental determination of aging, where always some number of discharge and charge cycles were performed, and then it was followed by this kind of procedure when from determining the impulse response and some other characteristics, or at Honeywell, the colleagues at Honeywell tried to determine the state of health of the battery. So the same cycle was implemented in our code, and for example, here we have 200 cycles. This is just the beginning when we can see this assessment, this whole assessment procedure, how the voltage evolves, and we can see simulation and experiment here. So basically, the pattern is very similar. This is the detail, and we can see some fitting of some, I don't know which one, the diffusion coefficient, which for some value we didn't get such a realistic profile. That's the red one, and then for the blue one, we got very close to the experiment already. And this is basically the final result for the assessment of aging, where for the most part we get quite a good agreement with the experiment. Only in the last phase, where really the battery deteriorates very quickly over just a small number of cycles, our model is still not able to predict that, which means here we are getting a disagreement. But on the other hand, even here, we need to basically stop using the cells in real applications, because otherwise we would be in for a disaster. Here we got during different cycles how the evolution of voltage looks like when the battery is new and when the battery is already degraded to some extent. The same one. So the first one was simulation. The other one is experiment. Again, the very last one, this one, is a little bit different than in the simulations, but otherwise we're getting quite a good agreement. And we also tried, just very quickly, simulations of battery packs when you have a parallel connection of more cells, and then you have to ensure that all the cells are basically at the same state of health. Otherwise, you would have reverse currents and you could destroy the cells, or which is usually implemented by connecting these cells by some very thin wires that can basically serve as a fuse when some of these cells deteriorate more quickly than the others. So we just got two of them, and we, for example, tested like one cell which was brand new, and the other one was at 90% state of health, and we applied some real driving cycle data which corresponded how the battery was charged and discharged during some driving experiment. And we saw that like the concentration of ions here, or the discharge, was different from, maybe this is not the one, I have one more, this is a simpler demonstration. Like the cell that was actually newer, or that was in a better condition, is the red one. It actually gets discharged much more deeply than the one that is already aged, and that can also cause a problem. And this kind of simulation can be done and determine when you are getting a problem. So when, for example, the battery pack is in for replacement because some of the cells are failing already. This is the same one with 180% state of health, and then the difference is even more pronounced. As you can see here, the H cell actually doesn't contribute almost, and the new one is excessively loaded. So this model, I think I have 3 minutes. Good. So this model was actually developed not for real-time use. It was a so-called high fidelity, which you've already heard today, high fidelity model, which had to be used for assessment of the more simple models that were developed at Honeywell during the project, which took place. And now the model is basically, after the project was finished, the model is used, hopefully, at Honeywell. And but unfortunately, Honeywell laboratory has moved from Prague somewhere to India, so we cannot collaborate with them anymore. These are the processes that are part of the model, and basically that's all. So thank you for attention.
Thank you for presentation and some questions.
I always have questions.
Welcome.
Thank you for nice talk. I have a question. You showed that the VOC curve you fit it. It's just mathematical, or there is a physical model for VOC curve also?
You mean open voltage?
Open circuit.
Open circuit.
Open circuit.
Yes.
Yeah, open circuit.
Well, at this time, it was really like an empirical formula that was fitted to the experiment, to the real battery, because we didn't have the data for most of the other parameters. We had literature-based data, but for this one, we had to really we needed to. For the open circuit potential to correspond to the real battery that we were using, and the producer of the battery was not willing to give us the data, so we had to fit it.
But in principle, you are able to calculate from basic physics this open circuit curve?
Well, I'm not sure.
Another question.
Maybe just misheard, but can you comment the speed of computation of this model? Is this like real time or
like 10 times real time, and it's already like maybe on the most modern hardware we would get even better performance. So I think like today, you know, like in every mobile phone you have a CPU fast enough to do this in real time, I think. So maybe in a car or in some system where you need it, like real-time control, you could also use this. But our main focus was on the aging, so which means that you need to do like hundreds of cycles, and you wanted it to run in some reasonable time.
So may I ask about the mechanisms of aging included in the model? So you talk about the solid electrolyte interface
Yes.
growth. That's one of them. Is there anything else?
In this model, it's just this one, but of course there are other, and there are also structural changes that occur in the cathode, which is not described in this model at all.
Okay.
So-
So for this model, the solid electrolyte interface contributes to both resistance increase and the capacity decrease at the
Yes, because actually in the solid electrolyte interface, the lithium ions are bound forever, and they can never take part in the reactions anymore.
Yeah, thank you.
So thank you again.
Thank you as well.